In the last episode, we talked about deferred functions in C++. We have learned how to implement asynchronous execution of the nodes in the NodeGraph. Let's see if we can do the same in Rust, following the same design pattern. I'm Sonia, and you're welcome in C++ versus Rust, where you will learn how to write parallel programs in Rust. Once again, welcome. This is C++ versus Rust, and we will be talking about deferred actions and parallel execution in Rust. Let's look at this graph. How do we execute this graph? First, we tell the source node to load the data. That will lock output pin and place the data in the output pin. Next, we tell the source node to process forwards. That will lock the output pin again. And first, we will send the data from that output pin to the connected pins. To do that, the output pin will iterate over the connected pins. The input pin of transfer node U goes first, and we send the data to that input pin. Then the input pin of transfer node V, and we send the data to that input pin. At this stage, input pins of both nodes have some data on it. Next, we propagate forwards, and we iterate over the connected pins again. First, we take the input pin of the transfer node U, and we take the owning node of that pin, which is transfer node U. We ask transfer node U to process forwards. Transfer node U returns to us a deferred action, and we start this deferred action. And then we go to the second input pin of the transfer node V, and we take the owning node of that pin, which is transfer node V. We tell that node to process forwards, and we receive another deferred action. Now we have two deferred actions. We return them to the user, and now the user runs deferred actions. The action for transfer node U and the action for transfer node V. The deferred action for transfer node U will first lock the input pin for reading. It will read the data from the input pin. It will apply the function to this data. Next, we lock the output pin of the transfer node U, and we set the data to be the result of that function. Next, we tell the output pin to propagate forwards. This will again iterate over connected pins, which is input pin of target node U, and we'll take the owning node, which is target node U. We'll tell that node to process forwards. The target node U will return to us a deferred action, and we return this deferred action to the user. Now we have this deferred action awaiting execution, and this other deferred action for transfer node V. However, this deferred action needs to execute straight after this one as a continuation, whereas this deferred action for transfer node V is independent and it can execute in parallel. Alright, the float for the deferred action for transfer node V is the same. The transfer node V will lock its input pin, will read the data from that input pin, apply the function to this data, lock its output pin, set the data on that output pin to the result of that function, send the data to the connected pins, which is input pin of the target node V. It will lock for writing this input pin and send the data, and then we'll propagate forwards. Again, iterate the connected pins, which is input pin of target node V, and we take the owning node, which is target node V, and we tell that node to process forwards, and that returns a deferred action. We return this deferred action. At this stage, both deferred actions, the one for transfer node U and the one for transfer node V, are fully executed. However, deferred action for transfer node U has yielded a continuation action, and deferred action for transfer node V yielded continuation action as well. So thread that was executing deferred action for transfer node U can continue executing the deferred action yielded from the execution of that action, and the thread that executed deferred action for transfer node V can now continue with deferred action that was yielded from that action. So we continue the execution of parallel threads with the new deferred actions. Alright, let's see how this is implemented in Rust. Alright, let's have a quick look how we implemented this in C++. We defined an actionable to be a variant of single, sequential, or parallel, and single is a function returning an action, sequential is a vector of actions, and parallel is a vector of actions. We defined action to be optional actionable. So single is a function which returns optional actionable, which can be single, sequential, or parallel. You can see this type is quite recursive. How can we define that in Rust? We can define that in Rust in exactly the same way. The std variant in C++ is equivalent to enum in Rust. So we can define single, sequential, and parallel in Rust in the same way. Single is a function that returns an action. Sequential is a vector of actions. And parallel is a vector of actions. And action is an option of actionable. We have the same definition in Rust using slightly different syntax, but it's exactly the same. We have also implemented similar helper functions. A defer action will turn any lambda into actionable single. The defer sequential will turn any vector of actions into actionable sequential. And deferred parallel will turn any vector of action into actionable parallel. So you have more or less the same implementation in Rust. In C++, the execution policy concept is a concept. We say anything that implements this concept has to be applicable to sequential and parallel. We can see that in Rust we use trait. Execution policy is a trait which is applicable to sequential and parallel. Let's look at this runActions function. It takes execution policy concept and action. It runs in a while loop as long as action has a value. There is 3 branches of execution. One that handles the single action, which is a function returning an action. If that function returns an action, it becomes the next action to be run in the loop. And another one which is sequential. We apply policy to sequential. And yet another one which is parallel. We apply policy to parallel. This is runActions implementation in Rust. It's very much the same. It's much more concise. Perhaps because I didn't log so much debug information. We can see it's a match between single, sequential, and parallel. For single, this match returns the result of calling the action, which is the next action to handle in this loop. In the case of a sequential action, we apply the policy. In the case of parallel action, we also apply the policy. We can see the implementation in Rust is almost identical. This is our implementation in C++ of the standard policy. This policy supports both running the deferred actions in sequential and parallel manner. It implements call operator for sequential by iterating over each deferred action and executing it using runActions. It also defines call operator for parallel. Depending on the const boolean whether we enable parallel or not, we will iterate over deferred actions in parallel or sequential. And for each action, we use runActions to execute them. In Rust, I have defined 2 separate policies. The basic policy, which runs actions in sequential manner, and Rayon policy, which runs actions in parallel manner. The base policy will run sequential actions by iterating over them and calling runActions. It will run parallel actions also by iterating over them and calling runActions. Very much the same as our C++ standard policy when enable parallel is false. The Rayon policy is parallel policy. However, apply sequential works still the same way. Iterate over all deferred actions and execute them using runActions. However, the difference is in apply parallel. The Rayon policy, when it runs actions in parallel, it uses parallel iterator. Into iterParallel creates parallel iterator, which will iterate over elements of the sequence and assign to them threads. And to execute each deferred action, we use runActions. We can see that the Rayon policy we define in Rust works the same as our C++ standard policy with enable parallel true. It looks like our Rust implementation doesn't differ a lot. Let's look at this C++ graph node definition. The process forwards and process backwards methods return an action. This is our definition of the graph node trait in Rust. And the process forwards and process backwards methods also return action. Let's look at the C++ code of process forwards method of source node. It returns a deferred action, which locks the output pin for reading, calls send data on it, calls propagate forwards on it, and returns the resulting deferred actions. Let's see the Rust version. This is the Rust version of the process forwards method of the source graph node. We can see it returns a deferred action, and that deferred action first locks the output pin for the reading. Then we send data, and then it calls propagate forwards on that pin and returns the resulting deferred actions. We can see that the structure of this deferred action is identical with the one in C++. We see this interesting capture list in C++ version. In C++ version we capture this. However, to prevent use after free, we also capture a shared pointer to this. Shared from this will give us a shared pointer to this, and we assign it to unused variable. Here we access the member field of this. This is why we have to capture this. If we don't capture shared pointer to this deferred action could be executed after the node is destructed. To prevent that, we do this capture. In Rust, we have a similar problem, and we have to solve it in a similar way. In Rust we don't have capture lists. Instead, we define a variable which is a clone of the output pin, meaning that we incremented reference count on the output pin, and we move that cloned pin into our deferred action so that we can use it there. This way we protect the lifetime of the pin, so that when this deferred action runs in a later time, we have a guarantee that this pin is still alive. We do not have the same data structure in Rust as we have in C++. The memory layout of our nodes in C++ is uniform. This is a piece of memory. And in that piece of memory we have both control block with shared count and weak count, and the node data. And inside of the node data we have read-write log. And inside of the read-write log we have output pin for the source node. So you can see that these all components live in the same block of memory. It's one uniform block of memory. In Rust it looks differently. In Rust we were not able to create such a construct. Instead, in Rust our nodes look slightly differently. A node is kept in an arc. Arc has very similar structure to shared pointer. The implementation of arc is actually using box, and inside of that box we have a control block and we have a data, which is our node. However, the read-write log with the pin in it is kept in a separate block, and it has its own control block and its own data. This is node and this is pin. So for example, source node has a field output pin, and that is a pointer to this control block here of this arc, which contains inside the pin. Now the pin inside contains a pointer to a node. It's a pointer to the control block of the memory storing the node. This is a weak pointer and this is an arc. Okay? So node owns the pin, is an owner of a pin, and pin knows the node, only knows, doesn't own it. So when we clone this arc into a local variable, we have a pointer to this control block storing the pin. We're preventing pin from dying, but we're not preventing node from dying. So this deferred action might be executed after the node is gone. But this is still safe because pin is using weak pointer to the node. Pin will know that the node is no longer available. So this is how this solution works in Rust. In C++ we don't have this problem, because in C++ the smart pointers have two fields. One is a pointer to the control block, and another is a pointer to the beginning of the data structure, in this case pin. So our smart pointer to the pin is owning the whole node, even though we only point to the pin. It's not the same as in Rust, because here pin is in a separate memory block. This is a special feature of C++ shared pointers. However, we can still implement exactly the same design as we see in Rust in C++. It just will be less efficient. So we could have design like this in C++, but this one is more efficient. Okay, let's run this example. We can see that the result of execution is correct. Still we get the same numbers as last time, 200.5, 1600.25. If we run in parallel, same numbers, nothing was broken. It ran without deadlocks. We can confirm that these values are correct by looking at the input, so 10 and 20. So we know that the first output will be multiplication, so that's 200, and the second is a division, which is 10 divided by 20, which is 0.5. And for backwards propagation, we use 20 and 80, and this gives us 1600 and 0.25. Alright, so our example works. Let's see how it works. So this is our example function. We create two policies, basic policy and Rayon policy. And then we have a helper function runGraph, which takes the policy. We run it for basic policy and Rayon policy. We do the same in C++ code. We call our helper function with standard policy false and standard policy true. Our helper function in C++ takes a policy of type implementing execution policy concept. Our Rust helper function takes a policy which is implementing execution policy trait. Very much the same. In our C++ version, we call source node process forwards and we pass the result to run actions with the policy. And we do the same in our Rust version. We call process forwards on the source node and we call run actions on the resulting actions. And we do the same for processing backwards. Although I can see that here in Rust, I run process backwards separately. I have two individual calls of process backwards, which will result in them being called sequentially. Whether here in C++ code, I have put them into deferred parallel action. And this will result in those two process backward method calls for these two nodes to run in parallel. Let's try that in Rust. Okay, so now we should be able to run process backwards on target node U and V in parallel. Let's see if that works. It worked in both cases, sequential and parallel. Alright, so this is our parallel version of running process backwards using deferred actions, which is identical with the C++ version. Alright, so we have implemented deferred actions in Rust, and we did it in the same way as we did it in C++. There wasn't so much difference in the code. Slightly different syntax, but that's it. Everything works the same. Comment, like, subscribe, and stay tuned for more episodes. Ciao!